On getting this far. So we just talked about basic chemistry, and we talked a little bit about compounds when we start adding together different elements. And today we're going to talk about a particular compound, and that is water. Water is extremely important to life for a lot of reasons. And so water is a compound, yes, but it is also a particular type, which we've talked about. It is not ionic. Remember, ionic is things like steel or rock or diamond. There is no transfer of electrons. It is covalent. And so there is a sharing of electrons here, which means that water has a sort of flexible bond. But the story goes a little farther, so we have to talk about polarity. So yes, covalent molecules do share electrons, but they do not always do so evenly. And that is because some molecules have atoms in them, like this oxygen, which has many more protons than the hydrogen. If I were to show you the periodic table, you would see that oxygen has an atomic number of 8, whereas hydrogen on the periodic table only has an atomic number of 1. And so you can see that oxygen has 8 protons, which are all positive, and the hydrogen has only 1 proton, which is positive. And so as you can tell, there's going to be more electrons attracted to the oxygen. And so yes, there are electrons, like let's say this one for example. It might be going between these two atoms, but it's going to be spending more time in the oxygen. So typically I will see chemists draw arrows like this to represent that, and you can see this is the positive side. And so this creates a partial charge, not a full charge, not like when we saw ions. Remember, when we saw ions, we were taking away electrons completely. So for example, if I had oxygen and I took away a single electron, that would make oxygen have a negative charge of 1. But I'm not taking away any electrons. Rather, we are just sharing them unevenly, and so we have partial charges. These partial charges are temporary, and they exist in only a moment. And so, for a brief moment, the oxygen might have more of the electrons than normal. We call this moment a dipole moment. Di means 2, and so as you can see here, there are 2 poles. There is this pole here, which is negative, and this pole, which is positive. And so this is a dipole moment. So what does pole mean? Pole, you can think about the Earth, right? The Earth has a north pole and a south pole. They are opposite ends. Likewise, there is a negative pole where there are more electrons, and then there's a positive pole where there are less. This dipole moment is brief, and so at one small moment, this partial negative charge will be here, and the next it'll be gone, and so will these. And then the next moment it will come back, and then it'll be gone. These moments happen quickly, and that's important. Okay, so usually I would have you drag these, but tell me, is it the hydrogens or the oxygen that is partially negative? That's right, the oxygen is partially negative because it is bigger and more electronegative, whereas the hydrogens are going to be partially positive during a dipole moment, but only for a moment, and then it's back to normal. During this brief moment, we can accomplish a hydrogen bond. So a hydrogen bond usually involves hydrogen, that's why it's called a hydrogen bond, but not always, just usually it does. A hydrogen bond occurs when there are two adjacent molecules which are polar and have during a dipole moment can attach. So this happens only in a moment. When both are having that moment, they can briefly attach. And so here you can see that there's a partial positive on this hydrogen and there's a partial negative on this oxygen. And so they're able to attach. But again, this is only for a moment. And so as quickly as these two molecules will join, they will unjoin. This creates a fluidity and why water can exist in a liquid state. It is because there is constantly dipole moments that are occurring and ending, meaning that water molecules continually attach and unattach. That is why they are fluid. And so, normally I would have you draw this. And I'm trying to think of, I'll just show you the answer. And so typically when we draw a hydrogen bond, we have to know what is the partial negative and what is the partial positive. And then we draw a dotted line. Now normally we have a line, right, as you can see with these oxygens and hydrogens. But a hydrogen bond is we're using a dotted line. And this is because it is a brief moment. That is why it's a dotted line. And so we consider this to be weak. It is a weak bond. That is one of the properties of a hydrogen bond. When we have water hydrogen bonding to itself, as you can see here with these dotted yellow lines, we call that cohesion. Without cohesion, water would simply evaporate. And so water needs to be a certain temperature to exist in a liquid state. If you were to, say, add heat to this, what you're going to do is vibrate the molecules in this water. That vibration means that those dipole moments I spoke of will be too brief. And so these individual water molecules will no longer be able to temporarily bind. It will lose its fluid-like state and we will get evaporation. If, however, it cools down again, if heat leaves, we get the opposite, which is condensation, and we will start getting those water molecules binding again. And actually, if you decrease heat enough, the water molecules will be vibrating so little that it forms a sort of solid, which you know as ice. So cohesion is between two similar substances. Whereas adhesion is when water can hydrogen bond, briefly, to another surface. The rule is that that surface must also be polar. H2O is polar. If the other thing, like this cobweb, is also polar, it will attach. But not all things are polar, as we will discover when we talk about cell membranes. An example of a nonpolar surface would be like a Teflon pan. A Teflon pan works so well because hydrogen bonding between it and your food is not likely. It is nonpolar, and so adhesion is not possible. And so here we see a test tube. And so what we have here, this U shape, is called a meniscus. And when we talk about lab procedures, you'll know that a meniscus occurs due to hydrogen bonding. And when we measure, we're trying to get a measurement, we measure from the bottom of the meniscus, not from the top. We measure from this dotted line, not from the top. And so, question for you, what type of force is causing this meniscus? Is it cohesion or is it adhesion? Well, the answer is kind of both. So actually it is adhesion to the glass. The glass is polar, but there's also water molecules stacking on top of each other, and that's cohesion. And so this comes, we're going to have a new term here, cohesion. Wait, I'm having a moment. Plus adhesion gives you capillary action. Capillary action is the combined force of cohesion and adhesion to create water columns that can go along a surface. And so here we see such a water column. This is how roots, for example, gather water from the ground. Okay, next we have mixtures. So water is really useful in mixtures. So a mixture is just a combination of two things. We have solutes, they are particles, and then we have solvents, which dissolve those particles or suspend them. And so we're mixing stuff in mixtures, very obvious. Next we have, oh right, I just said this. So again, solutes, solvents. Water, H2O, is the universal solvent, which just means that it dissolves most things. And the reason it is capable of doing that is through adhesion. Although hydrogen bonds are very weak individually, they are very strong collectively, so that even something like an ionic bond between sodium and chloride can be disrupted through weak hydrogen bonds. Just to recap, ionic bonds are strong. And then covalent are less strong. However, they're flexible. And then the weakest is hydrogen bonding, which is a type of covalent bond. Although hydrogen bonding is way weaker than an ionic bond, it can tear it apart if there's enough of them. And so when we put a grain of salt into water, it eventually will tear it apart. And so this is called a solution. A solution is created when you put something into water and it completely dissolves it. Compare that to a suspension. A suspension is when the solute does not completely dissolve. And so we see this oil here. It is not dissolving, it is floating. And so tell me, which is the suspension? Because we see the particles still floating, B is the suspension, whereas A is the solution. All right, so there is another quality to water we should discuss, and that is pH. So, oops, my bad. So pH is, I believe, potential hydrogen, I think, if I'm remembering correctly. So water looks like this. And the formula is H2O. That means there are 2 hydrogens for every oxygen. However, no body of water is completely perfect H2O. That is because water can dissociate into 2 parts. there can be a hydroxyl group, which is OH, with an extra electron riding along. And there's a hydrogen group, which we just call protium, because after all, a hydrogen minus an electron is just a proton. And so we get hydrogen and hydroxyl when this breaks apart. Coincidentally, if we added them back together, well, not coincidentally, it would be H2O again. And so in every single glass of water, bathtub, whatever, ocean, there is no perfect body of H2O. There's always some of each of these. And so the question then is, how much? Do we have more hydrogen or do we have more hydroxyl? In the middle of this scale here is perfect water, so this would be H2O, with none of either of the others in the mix. And then on the far left, we have acids. On the far right, we have base. So the scale goes from 1 to 14, and it tells you how much, I believe it's hydroxyl is in the solution. Each time you go up a number, you are increasing it by a certain magnitude, which I forget. I think it's to the 10th or something. And so here's all you need to remember. It goes alphabetically. Acid starts at 1, base is all the way at 14, and then perfect water is in the middle. If you are on the acid side, you have more hydrogen. If you're on the base side, you have more hydroxyl. And so an example of an acid would be like lemon juice, or even more so, car battery acid. And then on the far right here, we have stuff like bleach. Now, tell me please, what is this pH? Is this an acid or a base, or is it neutral? Again, that would be in the middle here, and that would be neutral. And then pH of 9, what's that going to be? That is past 7, and so again, it goes from acid to base. And so this would be a base. And a pH of 4 would be below 7, so that is an acid. pH of 6 is still just below 7, so that is an acid. What if you have more hydroxyl ions? That is a base. What if you have more hydrogen ions? That is an acid. Okay, so then what happens if we mix hydrogen with hydroxyl? You go back to water. And so you can counteract an acid with a base, and we call that buffering. Your body is equipped with buffers. So for example, if your stomach acid gets out of control, there is a certain cell, which I can't remember the name of, but this cell will secrete a base. Some people can't do this very well, especially as they get older, and so they lose their ability to buffer their own stomach acid, and they need to start taking things like Pepto-Bismol. Pepto-Bismol is a base which can reduce stomach acid and prevent you from having an upset stomach. All right, so that's pretty much it. See you next time.